All right.
All right. Our next speaker is Emanuele, who's a postdoc at MPI-SWS. Emanuele is on the job market for faculty positions, especially in Europe. So you should talk to Emanuele if you have such a job.
Yeah, thanks for that. Yeah, I'm Emanuele. I'm going to present work that I've done in cooperation with Azalea and Viktor. And it's about correctness of durable data structures. So we all know about RAM, memory. It's very fast to access, but of course has this drawback of losing all data when there's a power failure or simply we power it off. And we call such an event a crash in this talk. And of course, if you just have this as memory and you want to have your data persist across, you need to use some secondary means of storage, which is usually much slower to use. There's, as we've seen in the keynote by Viktor, new emergent technology that actually allows us to kind of marry the two goals of having almost as fast access and memory that survives the crashes. Now, we're interested in designing high-performance concurrent algorithms that work for both. And there's a huge literature on how to design them for RAM. And ideally, we would just want to use them on non-volatile RAM. Now, in an ideal world, we would have a non-volatile RAM that immediately persists every memory write. And in such case, we would have no problem. In reality, however, the writes do not persist immediately. And after a crash, we may observe in persistent memory some stale information together with some up-to-date information, and which can corrupt completely the invariance needed by the data structure to work correctly. And the hardware gives us, as the main tool, a flash operation that can force the persistency of writes on a specific location, but must be used sparingly, otherwise the performance just deteriorates. And so to have a concurrent data structure work on NVRAM so that it can survive these crashes, there needs to be some adaptation of the algorithm so that the flashes are issued appropriately so that when the power is resumed, the state is meaningful for the data structure to just resume operation. Now, we're interested in correctness of these data structures. And we may have already a proof of correctness for the data structure we are adapting from RAM to NVRAM. The problem is, and this is usually in the form of a linearizability proof. And ideally, we would want to also have some correctness transfer over the operation on NVRAM for the augmented code, but of course, just the linearizability proof that we have would not account for crashes. And so the idea of this paper is that just as the code is an adaptation of a volatile data structure, we would like the proof of correctness to be an adaptation of linearizability, not just an adaptation. We want to reuse the linearizability we already have proven for the volatile data structure and add some proof obligations that we call delta proof here that together with linearizability proof amount to durable linearizability, which is the stronger notion of linearizability that says that the data structure is correct even in the presence of crashes. So overall, with this structure for the proof technique, we obtain a proof technique that is modular in that it reuses the linearizability proof that we already had for the unmodified data structure. It's general in that we managed to provide this proof technique without fixing a particular weak memory model. And in fact, yeah, the reality is that there are buffers also that reorder the normal operation instructions, and we take that in account also in the non-volatile RAM model. Third, it's a technique that is powerful enough to verify the most advanced algorithms that have been published for non-volatile RAM. And finally, it's an incremental technique in that it's the difficulty of proving the proving the extra proof obligations is roughly proportional to how sophisticated the modification to the algorithm was. So to get into the details, I'm going to use a running example, a concurrent set implementation, the simplest I could think of for showing the issue. So we're going to see only insert and delete operations over a numeric key. And in particular, we're looking at insert. We're using a sorted linked list as the base data structure for representing the set. And here's the simplest code I could come up with for the insert operation. It's going to try again if the key is found in the set. And it starts, here I'm going to show you an example execution for inserting 5 in the data structure. It starts by traversing the data structure, the current data structure, to find the place where the number 5 should be inserted. Then, since it's not there, in its position we find 7, so we allocate a new node. And at the top, you're going to see these black dots. Those represent the memory operations as they appear in the trace. And then we initialize this new node with the key that we want to add to the set and the pointer to the next node. And finally, we link in the new node by swinging the pointer of the predecessor. Now, you'll notice that most of these memory operations don't really affect what the abstract set we are representing, right, is. It's 0, 7, 9 up until we finally swing this pointer of the predecessor, in which case the state becomes 0, 5, 7, 9 as desired. We call this point where this update in the abstract state happens the linearization point of the method. And more generally, we are looking at, when proving correctness of the data structure, we would be looking at an arbitrary concurrent execution where the threads call the operations of the data structure. And the proof technique for proving linearizability is to identify pair operation where this single point in time where the abstract state is updated is located in the execution. And this that induces a sequence on the calls. Because before they were overlapping, but the single points are ordered in an ambiguous way. And so the proof works by finding these linearization points, proving that there's only one per method, and proving that the induced sequence is indeed a legal sequence for the data structure. Here, for example, if we didn't have the delete in the middle of the two inserts, we would have a non-legal sequence because we would be inserting 5 twice, which is not part of the semantics of the set. And what this amounts to proving is linearizability, which intuitively is allowing the client to ignore completely the implementation details of the data structure and see every call as a single atomic event ordered in some legal sequence. So imagine we've proven linearizability for the data structure as sketched. What can go wrong when we run it on non-volatile RAM? What happens if there is a crash? Well, this kind of happens. I think this is a pretty accurate description that Dali already foresaw in 1931. And I didn't even need to change the title. The title is The Persistence of Memory. So it was just a vision. And to go more in detail, what happens when there's a crash is determined by the persistency model. So the memory model specifies the so-called non-volatile order between events. This is the order in which each event was scheduled to be persisted. Right? For example, here I have a number of events and they were scheduled this way to be persisted. And if a crash happens after the first 3 were persisted, then the rest would be just lost. and when we resume operation, those events will just not have left a trace. And the catch is that the volatile order of execution and the non-volatile order do not need to necessarily agree. They only need to agree on writes on the same cache line. And in this example, that means on the same node. So in this example at the bottom, if we are writing to N and we are writing to P in this order, the underlying hardware can decide to persist the write to P first and then to persist the write to N. For the example trace we looked at in the data structure, this means that this is a feasible scheduling for persisting the writes. We would first allocate the node. So here at the bottom, I'm reordering the events according to the non-volatile order. So we would first allocate the node, and then swing in the pointer of the predecessor, and only then initializing the new node. And of course, this is problematic, because if a crash happens before the last event is persisted, we would end up in a completely inconsistent state. We have 7 and 9 are no longer reachable from the head, and moreover, we forgot we lost information about which key was added to the set. So it's a completely irredeemable situation. So what can we do to fix this? So this would be a tool that we use to modify the algorithm, right? The hardware allows us to flush locations explicitly, and flushing X makes previous writes on X persist as soon as flush is executed. Moreover, any write after the flush will be persisted after the flush completed. So to fix the order between these two instruction at the bottom, two writes at the bottom, we can issue a flush just after writing to N. A flush of N would make sure that the write to N is persisted and that the later write to P is persisted afterwards. And so for this trace, we could use the flushes to enforce that the scheduling agrees with the execution order by flushing the initialization as soon as we are done with it and before swinging the pointer of the predecessor. And we would also want to issue a flush of the pointer of the predecessor before returning, so that we make sure that when we return to the client, this operation is persisted in memory. So one question as a designer of the algorithm is, what are the flushes that are necessary? And because we don't want to put too many of them, or the performance would degrade, right? So the brute force approach is flush everywhere. Flush after each write to persist the write, and flush after you read a write so that you avoid getting ahead of what the persistent memory is. And this is really bad for performance. And actually, one can do better. And if we look at an example execution of the insert of 5 in this particular state, we would start by traversing the data structure, then inserting the new node. And while we traversed, we witnessed the presence of many elements, but the presence or absence of these keys in the set are completely irrelevant for establishing whether the insert was correct or not. Right? The only thing that matters is whether 5 was there or not. And in the literature, there is an algorithm called NV traverse, which was proposed in 2020. And it capitalizes on this observation that during the traversal, the flushes are not needed, and only flushes around the linearization points. And it achieves better performance, but the chief concern of this paper is, how do we prove correctness of this kind of optimizations? So if we look at an example trace again for the same data structure, we could be inserting 5, and concurrently there's an insert of 1 and an insert of 2. And so it happens that the traversal observes them, right? So we go through the list and we witness that 1 and 2 are in the set. And this is the snapshot of the memory that we are using to support the argument that inserting 5 now is correct, because 5 is not in the set. Now, because all of these inserts are operating on different nodes, they can actually be scheduled to be persisted in a different way, right? In the opposite order, for that matter. And here I'm putting them in that order at the bottom. And the issue is that when you try to justify why the data structure can survive a crash, you need to justify why having an insert of 5 persist first before the other 2 is correct. And the view that you have, like the contents of the persisted memory when insert 5 is persisted is actually not containing 1 and 2. And so there is a gap between what the volatile traversal witnessed and is reasoning about and what you actually have in persistent memory at that moment. And a naive approach would be to try to prove that this gap does not grow too large and that essential features of the invariants are preserved between the two views of the memory. But as you optimize your code, this gap grows larger and larger, and it's very, very difficult to pinpoint, right? And furthermore, this approach does not really follow the rationale for the optimization in the first place. The optimization was justified by this intuition that certain things were independent. So what we propose instead is to start from a vanilla linearizability proof. In particular, we reason on volatile memory, and so that's the structure that we will use to justify why the insert of 5 is correct in this case. And add to it some proof obligations, right? What would this look like? In essence, they look at the calls, at the linearization points of the calls, and allow the volatile order to be contradicted by the non-volatile order on the linearization points, only if the two calls abstractly commute, which means that as far as the set semantics is concerned, their order doesn't matter. And for example, for an insert of 2 and an insert of 5, the order in which they are executed would not matter for a set. And in fact, this means that our proof obligation would allow this to happen in the execution. Instead, the proof obligation also forces us to consider the pairs of calls that do not commute, like an insert of a key and its deletion. And it would force us to put flushes between these two so that the order between them is actually agreeing in the two, in VO and NVO. Our crucial result is that if these two are true, you can conclude that the NVO respecting sequence of linearization points is legal. It's a valid sequence of operations for the set semantics. And crucially, this implies that the set at the beginning here does not contain 5, otherwise this would not be a legal sequence. And this is extracted from this legality. It's a consequence of having proven these proof obligations in addition to linearizability, and we never needed to establish this link between what's persisted and what's in volatile memory explicitly. So the key idea is to base the proof on these commutativity properties. And the proof obligations that you get are trivially true when you aggressively flush, because flushing aligns the two orders, right? And becomes more and more difficult as you remove flushes. And another nice property of this strategy is that delta proof can be read as a design principle for the data structure or for the optimizations. You only need flushes that enforce ordering between non-commuting calls. And the main theorem that we call the Pathway Theorem, because it takes you from linearizability to durable linearizability, says that this is enough to entail durable linearizability. Of course, I simplified a lot in this presentation. The proof principle in the paper is more powerful than this. The delta proof that we have in the paper is more general than this. The recovery procedure is also taken into account, and its proof is nicely decoupled from the main proof of the algorithm. The technique also supports more advanced algorithms where the volatile representation of the data structure and the persistent representation may significantly differ, in which case the points where the linearization seems to take effect and the persistent takes effect may not even be the same event. And so the gap between the volatile and persistent contents may be even wider. And we applied the methodology to the link-free set presented at Uppsala in 2019, where all these techniques are employed to get a very performant data structure. And the proof is, it requires a lot of advanced techniques. It needs supports for helping, speculation, and insight, which are all hindsight, which are all things that we support in our proof technique. It also supports algorithms where the volatile state can lag behind the persistent one, as opposed to what we've seen in the presentation. And finally, we support weak memory models by relaxing what this volatile execution order can be. And if you're curious about what happens in a crash, when there's also weak memory in the mix, Dali also had a vision about that 20 years later. With the disintegration of the persistence of memory. So this is our paper. We get a technique that can reuse the linearizability argument, does not fix the memory model, can handle advanced algorithms, and it's proportional to the difficulty of the modification of the algorithm. And in the future, we want to turn it into a program logic for durable linearizability. Thank you.
All right, thank you for the surprisingly entertaining linearizability talk.
My name is Jiyoon Kang from KAIST. It seems that you assume the programming model of NB traverse where the operations are split into read phase and write phase. So I wonder if your story scales to those data structure set doesn't specify these assumptions like Harris-Michaels list, for example.
Yeah, so our technique is definitely not tied to that structure. I used NV traverse to give an illustration of a simple optimization that still shows the problem we're trying to solve. But in fact, the link-free set that we verified relies on much more advanced techniques. And we do not rely on any specific structure for the algorithm, and we don't focus on sets for that matter or collection. It's just a general technique that applies to the semantics of the program and shows that those proof obligations are enough to deduce durable linearizability from linearizability. So it's really independent of which is the algorithm that you're.
So from your answer, I assume that you are splitting the helping cases and the linearization point cases in the proof, or do you somehow specially deal with the helping cases of Harris-Michaels list, for example?
There is some machinery that is needed to support things like hindsight linearization and helping and speculation, yes, but it's all embedded in the formalization of what the linearization proof is. So we allow the linearization proof to be based on these advanced techniques, and we can build on that to define what the delta proof should be.
Other questions? Okay, I think let's thank the speaker again. We'll move to the next talk.